So I think it's a good idea for our first attempt at understanding what a classification problem looks like is to take the easiest one. And for that, there's no better place to start than cyclic groups. This is actually one of the reasons people study them first, is that they are especially easy to classify. So the idea is that this shouldn't be too unexpected because any cyclic group, all of its elements are uniquely nailed down by a single element, a generator, right? So somehow one generator, one element describes the entire group. And since only one thing is controlling the whole group, that sort of makes them easier to understand, okay? So what I want to do is walk you through the classification of all cyclic groups, and it ends up being a really nice answer. This is another reason why people care, is that not only are they easy to classify, the answer is very, very nice. And it turns out that cyclic groups are completely classifiable. You can totally characterize them solely based on their size, how many elements they have, okay? And that's all you need. So the only data you ever need to classify a cyclic group is how big it is, and that's it. And in fact, we can easily give models. The models are going to be the cyclic groups you already know about. There's the infinite cyclic group Z, and then we have the finite cyclic groups Z mod N. And a consequence of this classification is going to be that this is the whole list, right? So we actually know everything there is to know about cyclic groups simply by studying Z and studying Z mod N, okay? So let's walk through the proof of this. How do you prove such a classification statement, right? Well, here's the biggest step. The biggest, most important step is theorem one. Suppose that G is a cyclic group. I claim that one of two things happens, okay? If G is infinite, then I claim that it must be isomorphic to Z. If G is finite and has n elements in it, so the order of G is n, then I claim that G must be isomorphic to Z mod n. Okay? And this should prove that given any cyclic group and given its size, there's only one isomorphism type because you know what the answer is, right? If I gave you a cyclic group of order 14, then the verdict is it must be isomorphic to Z mod 14, and there are no other options. So the classification of cyclic groups is there is a unique cyclic group up to isomorphism type given the group's size. Okay, so let's prove this. The proof has to come in cases since the theorem itself is for use in cases. So since G is cyclic, that's the standing assumption here, is that G is cyclic. We know that there must be an element A in G that generates the entire group. So let's just suppose we've chosen a generator at the beginning and we're going to stick with that generator all the way through. So suppose throughout the proof that G is generated by A. Right? So the easiest part of the proof is actually step one, case one, where the group is infinite. And it might be strange that the infinite case is easier than the finite case, but I'll point out why that's true as we go through this. Suppose that G is infinite. Well, that means that the generator has to have infinite order as an element of the group. And we had a theorem from class, this is back when we were actually meeting face to face, that tells you when the order of A is infinite, then all the powers of A are different from each other. That is, if you wrote down all the powers of A, both the positive powers and the negative powers, there's never any redundancies. They're all different, okay? And that means that G consists of all these elements. And this is a unique, this is important, unique description of the elements of G. So what I'm going to do is I'm going to give this unique description of the elements of G to give you an isomorphism from G to Z. That's my job after all, is to prove that there's an iso from G to Z. Now it's easy. You know what the iso is going to be? If you look at this list of elements of G, do you see integers? I do. It's the exponents. 0, 1, 2, 3, 4, etc. And then -1, -2, -3, -4, etc. So the isomorphism is take an element of G, which is expressible as an a to the k, right? Everybody is, and map it to its power, which is k, and that's an integer. And since everybody in G is uniquely expressible as a to the k, then this function is well defined, right? This unique expressibility as a power of k will not happen in the finite case, and that's why the finite case is harder. So by taking my element a to the k and just writing it with its exponent only, that's my integer, and that's going to be my isomorphism, but I need to prove that this is an isomorphism. That means I need to prove that my alpha is a homomorphism, and that is 1-to-1, and that is onto. Right? The fact that alpha is a homomorphism is clear because that's just the law of exponents. So what's alpha of two things multiplied in G? Well, two generic things in G are an a to the k and an a to the j. But a to the k, a to the j is a to the k plus j. And what's alpha of that? Well, it rips off the exponent, so that's k plus j. But k is alpha of a to the k because it rips off the exponent. And j is alpha a to the j because it rips off the exponent. And therefore, alpha of a to the k, a to the j is equal to alpha of a to the k plus, that's the operation in Z, by the way, is plus alpha a to the j. So it's a homomorphism. That's not hard. That alpha is onto is obvious. If you give me anybody in the integers, then a to the k will hit it. And injectivity is clear. If alpha of a to the k is alpha of a to the j, that says that the exponents are equal. But if k is j, then a to the k is equal to a to the j. And so the inputs had to be equal. And so there you go. Alpha from G to Z is an isomorphism. Okay. So the proof in the finite case, the proof here is nearly the same, except you don't have this uniqueness when you write down all the powers of A, because the powers of A, remember, at some point loop back around and they start to repeat themselves. And because you get that repetition, the proof's going to be a little bit harder. So let's go through the proof of why this still works if G is finite. So suppose that G is generated by A, okay, and A is going to have to be a finite order element of order n because the same thing is true for G. Well, we had a theorem from class again, back when we met face to face, that says when the order of A is n, this is your complete list of elements with no redundancies. A to the 0th, A to the 1st, A squared, A cubed, up to the A to the n minus 1 are all different, but then A to the n loops back around and is the identity, and A to the n plus 1 is A, and A to the n plus 2 is A squared, and so on, right? So that's the problem. It's possible that A to the j is equal to A to the k, even though j and k are not equal, okay? Let's make sure we understand that. We've seen this a million times before in class. Suppose the order of A was 10, so my group G was cyclic order 10. So order of A is 10. That means my elements are the identity up to A to the 9th. Those are all my distinct guys. Well, A to the 8th is legitimate, and A to the 5th is legitimate, but their product is A to the 13th. And A to the 13th would not be on my list of E up to A to the 9th, right? But the point is, well, it is, but it's A cubed, right? Because A to the 10th is the identity. So A to the 13th is A to the 10th times A cubed. And so that's A cubed again. And of course, 3 is the remainder, the power here, the cube, is the remainder of the answer, 13 divided by 10, which is going to be the right answer. So we got to do this by long division. So we got to adjust our proof to compensate for the long division that we have to do. Okay, so here we go. Here's how we do it. Define a function that goes from G to Z mod n as follows. Well, look, Z mod n has elements 0 to n minus 1, right? That's what Z mod n is. And notice that's exactly the exponents here. Exponent 0, 1, 2, up to n minus 1. So I can do the same thing and just rip off the exponent, right? So if I give you an x in G, it's uniquely expressible as a to the k for some exponent that you chose to be small enough. Then I can define alpha of x to be alpha of a to the k to be the exponent k. And k from 0 to n minus 1 is a legitimate congruence class in Zn, right? And so because I chose k correctly, alpha is well defined. That's not a problem. The problem is it still an isomorphism? We got to think about this a little bit. The hard part is actually getting that it's a homomorphism. After that, it's easy to show it's 1-to-1 and onto. But the hard part is that it's still a homomorphism. Okay, so let's do it. Take two generic elements from G. Well, two generic elements from G are writable as a to the k and a to the j, where k and j were chosen to be in the same span from 0 to n minus 1. Right? The only problem is when you multiply them, the exponent is going to be k plus j, which could be too big, like 13, so we got a long divide. So let r be the remainder of the new exponent k plus j upon division by the modulus n. Right? So look, when n is 10 and the exponent is 13, r is 3. That's exactly the story we had up here. Right? Please note that when you work mod 10, k plus j 13 is equal to 3, so that's why you have to use a z mod n right here. Okay, it makes it work out right. So as usual, when we long divide, that means that k plus j is nq plus r, where the remainder, look at this, was chosen to be small enough. And look, that remainder lives in the same span for z mod n. So it's clear that a to the k plus j is a to the r because the nth power will be the identity element. And so what is alpha of a to the k, a to the j? That's alpha of a to the k plus j. But you got to write that exponent to be in the correct span, and when you do that, it's exponent r. So this is alpha of a to the r, and so alpha of a to the r is equal to r. So where does a to the k times a to the j go? It does not go to k plus j. It goes to r. It goes to r by the way we've defined alpha. On the other hand, right, that's one side of the homomorphism equation. The other half is what's alpha a to the k plus alpha a to the j. Well, that's a correctly chosen exponent, so it's k. That was correctly chosen, so it's j, so it's k plus j. But we're in z mod n, and in z mod n, k plus j is equal to nq plus r, but n is 0, so you get r back, and that's exactly this. So it is true. Look, there it is. It is true that alpha is a homomorphism, but that's only because we landed in z mod n this time. The proof that alpha is 1-to-1 and onto is exactly the same as before, and so there you go. Alpha is your isomorphism. Okay? So now we're done. We can actually use this theorem to give an immediate proof that there is there's only one isomorphism type of cyclic group for any size. Right? So here we go. Any two cyclic groups of the same size must be isomorphic. They must be. So we're proving there's only one isomorphism class when you have cyclic groups of a given size. Any two of the same size, as long as they're cyclic, must already be isomorphic. And here's the proof. It's simple now. It's only 3 sentences. Let G and L be cyclic groups of the same size. So the order of G is the order of L. If they're both infinite, then the theorem we just proved proves that they're both isomorphic to Z. But isomorphism is a transitive relation, and therefore G and L are isomorphic. Right? And if they're both finite of order n, then the same theorem tells us they're both isomorphic to Z mod n, and by transitivity, they're equal. Okay? So now we're done. Now we see that we have achieved a complete classification of cyclic groups. If G is infinite cyclic, it must be Z. If G is finite of order n and cyclic, it must be Z mod n. Okay? This also works for the trivial group, which is cyclic. The trivial group is cyclic, and you can regard that as Z mod 1 if you like. Many people do. So hence we have proven there is precisely one isomorphism type among cyclic groups of order n or of order infinity.